Hello and welcome to this video about creating a simple artificial neural network for image recognition. In this video, we'll look at how to create a simple artificial neural network from scratch and not go into concepts like convolutional neural network for image recognition. So consider this as a beginner's tutorial for using artificial neural networks using TensorFlow and Keras. So let's get started. The first thing we'll do is import all the relevant libraries. Next, let's talk about the data that we'll be using. We will be using MNIST data. MNIST is a data set of images of handwritten digits from 0 to 9, and the objective is to identify what is the digit written on each of these images using some machine learning tasks. Keras has a function which allows you to download and load the MNIST dataset directly into your notebook. So we'll use that function and we'll get all the X variables and Y variables of our training and test dataset directly into our notebook as these variables. Let's look at how many images do we have in our dataset and also the dimension of each of these images. We'll use the shape attribute here on our variables. So you can see there are 60,000 images in our training dataset and 10,000 images in our test dataset. The dimension of each image is 28 cross 28. So we have a 2D image with dimensions 28 cross 28. Let's now look at our independent X variable to see how the data actually looks like. We want to see how the first image looks like, how the individual pixels appear. So we call xtrain brackets 0 and we see a 2D array of all the pixel values that we have in this image. You can see the pixel values are between 0 and 255. A value of 0 denotes a black pixel and a value of 255 denotes a white pixel. Next, we can also see the Y dependent variable. So I have here shown the first 5 values of the training data set in terms of the dependent variables. So we have values which is 5, 0, 4, 1 and 9. If you look at the entire data, the dependent variable will have values between 0 and 9, which are the labels that we want to predict. Let's look at both of these things together for one particular image. So we are taking index 2 and looking at Y variable and the X variable. When we see the Y variable of index 2, we can see the value is 4. And if we use matplotlib's imshow function and pass the X train with index 2, we see the image which is also 4. Right? So this is how your image will look like and this is how your labels will look like. Okay, before we start training and evaluating our model, the first thing we need to do is to do some pre-processing in the form of min-max normalization. You know that the pixel values in our data are between 0 and 255, but artificial neural network work best if the values are between 0 and 1. Therefore, we'll do a min-max normalization. The max value in our data is 255 and the minimum is 0. So we can do it simply by dividing each pixel by 255, and that is what we have done. So the pre-processing and the min-max normalization step here is pretty simple. Okay, once we have done this, let's now go to defining our model structure and then we'll go to training. So first, to define our model structure, we need to create a variable to store the dimensions of our input image. We can directly use the shape attribute, and you already know this, that the dimension of our input image is 28 cross 28, which is stored in this variable called ImageDim. This ImageDim variable we'll use in the next step, where we are defining the actual model structure. Because we are creating a sequential artificial neural networks, we'll use keras.sequential and specify all the layers that we want in our neural network. The first layer is a flattened layer. We know that our image is a 2D image, but we want to feed in a 1D image, right? So that is what flattened layer does. It takes our image, which is a 2-dimensional image of 28 cross 28 that we have specified here. Input shape is equal to ImageDim, and then flattens it into a 1-dimensional image, right? The next layer is a dense layer of 100 neurons. That is what we have specified here, and the activation function that we have specified is ReLU. ReLU is a function which takes a particular value and returns 0 if the value is less than 0 and returns the same number if the value is above 0. Right, so that is our activation function for this dense layer. We also introduce a dropout layer. Dropout layers are introduced to prevent overfitting. In this case, we have passed a value of 0.2 to our dropout layer, which means 20% of all the neurons in the previous layer will be deactivated randomly so as to prevent overfitting. The final layer is a dense layer of 10 neurons. Why do we have 10 neurons here? Is because we have 10 different labels for our image. We have digits from value 0 to 9, and each individual neurons will give a score associated with each of these labels. So the first neuron will give us the score associated with the image being 0. Right now, we want these scores to actually represent the probabilities, and that is why the activation function that we'll use is softmax. What this will do is it will make sure that the first neurons gives out a value which represents the probability of this image being 0. The second neuron gives out the probability of this image being 1, and so on. Right. So now that we have defined our model structure, we can call a function which is compile. Here we specify our optimizer, which is Adam, the loss function that we'll be using, which is sparse categorical cross entropy, and the metrics that we'll be using, which is accuracy. So for every iteration will be shown the value of accuracy. Right. At this point, we have specified our model structure, so we can start training the model. So we'll call the fit function, pass the training data's x variables and y variables, and specify how many iterations do we want. So epochs is 5, so we have 5 different iterations on our training data. As you see, the number of iterations are going up, the loss is going down, and the accuracy is increasing, and the final accuracy that we see on the training data set is around 97%. We can now check the performance of our model, the artificial neural network model that we have created, on test data, and we'll do it in a couple of different ways. First, we'll check the performance on the entire test data, and then we'll look at predictions of individual image. So let's first see the performance on entire test data. We use a function which is evaluate, pass the x variable and y variables of our test data, and we'll see the final accuracy that we get is 97.5%, which is very close to the accuracy that we had in the training data, so not a very bad model. Okay, the next thing that we can do is we can look at prediction for individual test samples. So we'll take the test data and look at what are the predictions for index is equal to 1. First, look at what is the actual label that we have for index is equal to 1. That value is 2. And you can see how the image also look like. Image is also of 2. So the labeled is 2 and image is of 2. So we would want the predictions to be also 2. To get the predictions for this test data, we can call predict function. But this predict function requires all of our test data, so we'll pass the entire test data x variables that we have, and y test predict will have the predictions for all the images in that test data. We just want the predictions for index is equal to 1, so that is what we do. We pass index is equal to 1, and this is the array that we get in return. This array has 10 different values, and these represent the probability of the image being 0, 1, 2, and so on. Right now, these values are in exponential format, so slightly difficult to read. What I've done is I've formatted in a decimal format, and you can see that now it's slightly easier to read. The first value is the probability of image being a 0, second value is the probability of image being 1, and third value is the probability of image being 2. And as you can expect, this is where we want the probability to be the highest, because our image is actually of 2, and we can see the probability is actually very high here. We can convert all these prediction probability into one final label that we want for this image. We can use NumPy's argmax function, which takes all these 10 values and gives us the index where the value is maximum. The index where this value is maximum is 2, and that is what we want, and this is the label that we want. We can replicate the same process for all the data that we have for tests. So we have all the test predictions, we loop over them, call NumPy's argmax function, and this will give us predicted labels for all our test data. Here are the first 5 values, 7, 2, 1, 0, and 4. Okay, now that we have predicted labels for our entire test data, we can create a confusion matrix. In TensorFlow, we have a nifty little function which is tensorflow.math.confusion matrix, where we pass the actual true labels and the predicted labels, and this gives us a confusion matrix here. The x-axis here is the predicted labels, so this is the predicted labels, and the y-axis are the true labels. So how do we read this? The first row here represents all the images which have 0 in them, so the true label is 0. 969 of these images were predicted to be 0, but 5 of these images were predicted to be 6. So these are wrong predictions. And as you would expect, most of these values, most of the values in this confusion matrix are along the diagonal, which is what we would expect. These are all correct predictions. Everything which is not on the diagonal are wrong, incorrect predictions. Right? Okay, apart from confusion matrix, we can also use scikit-learn's classification report function to give precision recall F1 score for all of our labels. Okay, the final thing that I want to touch upon is TensorBoard. TensorBoard is a tool that can be used to visualize the performance while we are training a particular neural network model using TensorFlow. So how do we use it? First thing we need to do is we need to specify a location, a path where all of our logs from training will be stored. I've created this variable logs_dir which specifies the path where the logs from training will be stored. Inside this, I have specified the current timestamp. What this means is every time I run this notebook again, what it will do is it will create a new folder based on the current timestamp, so that I have separate logs for every run of this training process. This logs directory will be passed to this particular function, callbacks.tensorboard. So we specified logs directory and a few other parameters, and this is what creates our TensorBoard callback, which we'll be using while we are training the model. That is what we do next. We repeat the exact same process that we did earlier. We define the model structure, the 4 layers in our neural network. We do model.compile. And when we now do model.fit, apart from passing the x variable and y variables of our training data and the epochs, we also specify the callbacks. In this case, we are specifying tb.callback, which we defined earlier. Right? So this will actually create the data in logs directory, and that is what we can use to visualize in our TensorBoard. You can open TensorBoard separately in a new tab, but you can also use this magic from notebook, Jupyter Notebook, to visualize TensorBoard within your notebook. So there are a lot of things that you can explore here. I will just touch upon one of this. So what this graph shows is what is the performance on the training data as the number of iterations increase, as the epochs increase. I have multiple runs here, so you can look at each individual runs. In my case, the 2 runs did not have different parameters, so the values and the performance is almost the same. But let's say you are changing the optimizer and want to see how the performance differs. You can have multiple runs and compare the performance. There are several different tabs, so you can explore them, look at histograms and distribution and so on. But for now, I will limit it to just this. I think that is it from my side. If you have any questions or comments, please feel free to enter them in the comment section below. Thank you for watching the video.